So when I'm trying to solve an equation involving modular arithmetic, my goal in solving this is to find a number that effectively divides by 89. So it turns out we call this number t a multiplicative inverse. Now that's specific to the fact that I'm working mod 232. So t is a multiplicative inverse for 89 in the mod 232 world. In general, if I want to solve an equation that looks like this, I need to find the multiplicative inverse for A. So when can I do this? When can't I? Well, there's a very nice theorem. If the greatest common divisor of A and M is 1, then A has not just a multiplicative inverse, but a unique multiplicative inverse, mod M. And it turns out that the reason this is true is our Bézier coefficients, which we got by doing the Euclidean algorithm. So the number that is the inverse is the number that comes from doing the Euclidean algorithm and the Bézier coefficients, which together are known as the extended Euclidean algorithm. So in order for me to solve that equation I started with, 89x equals 1, what I need to do is I need to find that multiplicative inverse. I only know this will work if the greatest common divisor of 89 and 232 is 1. So I want you to do the Euclidean algorithm to compute the greatest common divisor here. So let's go back to what we were doing on Monday. How do I find this greatest common divisor using the Euclidean algorithm? I need a quotient and a remainder. Now you could do the entire calculation of greatest common divisor on your calculator, but knowing that the greatest common divisor should be 1 doesn't help me get the inverse. I need all the steps to do the Bézier coefficient crap that we did on Monday. So, walk me through this. What times 89 plus what? which means the next step is to do 89 is something times 54 with something left over. But there's only one 54 in 89, and the leftover is keep going. 54 over here, 35 as my divisor. I keep going until the remainder is 0. How many 35s with what left over? Repeat the process. 35 is some number of 19s with something left over.
One plus 16.
19 is so many 16s with so much left over. 16 is so many 3s with something left over. And 3 is 3 1s with nothing left over. That's my stop condition. And that means that the greatest common divisor is 1. It's the number we last divided by, which is the same as the remainder on the previous line. That means we have an inverse. Please note, all this calculation just showed me we can get one. How do I get one? I have to write 1 in terms of 89 and 232, which means I need to work my way back up all of these equations. So let's start with this one. 1 is 16 minus 5 3s. 3 is the remainder in the line above that. So rewrite that equation to be 3 equals. Three is 19 minus 16. Replace that inside this set of parentheses. And regroup. How many 16s? How many 19s? I have 6 16s and minus 5 19s. Doesn't matter which order you put them. But 16 is the remainder in the line above that. So let's rewrite that line to get 16 all alone. Sixteen is 35 minus 19. That's what this line right here says. Replace that set of 16s with this set of numbers. And regroup. How many 19s and how many 35s? How many 35s do I get? Say again? I get 6 of them, right? Because this is minus 5 times 19 plus 6 times 35 minus 6 times 19. So I have 6 35s and how many 19s? Minus 5 of them and minus 6 of them makes minus 11 of them. 19 is a remainder in one of my equations. This equation right here. Rewrite that equation to get 19 all alone. Nineteen is 54 minus 35. Put that here. And regroup. How many 54s? How many 35s? Minus 5 here?
You have 635 and then minus 1135.
Hang on, there's another minus in there.
Oh, you have to distribute that.
Right.
17.
So there are 17 35s and minus 11 54s. 35, the smaller number, is a remainder in one of my equations. As a matter of fact, it's a remainder in the next one up. So let's get that all alone. 35 was 89 minus 54. Replace your 35 with 89s and 54s. How many 89s? How many 54s?
Six. What was it? Minus.
It'll be minus 17 minus 11.
Okay.
It'll be minus 28 of them. The numbers I want are 232 and 89. 54 is the remainder in the very first division we did, which means this next step is the last friggin' step. 54 is 232 minus 2 times 89. So that 54 gets replaced by this. How many 89s? How many 232s? All is said and done. Here is where the distribution becomes important. $28 times 2 is 56. 56 and 17 is 73. That's the number I want. I claim if you multiply 73 and 89, the result is congruent to 1 mod 232. So do me a favor, grab your calculators, and tell me, what's 73 times 89? Divide that by 232. Your quotient is, when you do that division, the numbers before the decimal place is 28. Look at this number right here. What's 6497 minus 28 times 232? What's the remainder? 1. So here's what this means. If I encode with 89, you decode with 73. I would like you to solve the following problem. If I were not working mod 232, the answer would be divide. Divide by 89. I don't know how to divide by 89. So instead, I will multiply by the inverse. We just worked out the inverse is 73. So the correct way to cancel out that 89 is to multiply both sides of this equation by 73. Because over on the left-hand side, 73 times 89 is 1 mod 232. So on this side, this becomes 1. Which means I get x equals. X equals what? Well, what's 73 times 15? Now do that, mod 232. What is the quotient and the remainder? It most certainly would. Public key encryption means you put out there a number. Everybody gets to see it. And that's how they encode a message that gets sent to you. But only you know your decryption code. And what they do is they take the message they want to send and encrypt it with the number you put out there in public. And this number is out there too. And then you get the message 15, and you go, gee, I wonder what they really said. And they said this. And you decrypt it with your key. Now, these are really small numbers. We did all this calculation by hand. On my computer, these numbers are 200 digits long. They're usually not even numbers, they're hex. So they look like passwords. And when you go to encrypt something to me, you run it through a password hasher. And it does all the encryption for us. I get the message, and I click my button, which has my key in it, and I see the message. Right now, in my email, I have an encryption algorithm built into my email called Virtu, V-I-R-T-U. Anyone can install this on Gmail. When I am sending student information to the registrar, or they are sending me information with student ID numbers and grades and other that information shouldn't be out there in the public, right? They encrypt it. The Virtu key is tied to my email. All I have to do is push one button on my Gmail account. It does the decryption. It does it like this. And the only reason this works so quickly is because I could do all of this. This, Bezout coefficients, and the extended Euclidean algorithm are the foundational pieces of modern encryption. Useless, people were never going to use it anyway. Every damn day. Every credit card transaction in the world is hidden this way. Questions? What we've just done is equivalent to solving a linear equation. Number times x equals another number, right? Only we did it mod something. I learned how to do linear equations in my first algebra class, right? 3x plus 6 equals 0, solve for x. I remember that. And then a couple of chapters later, we did simultaneous equations. Remember stuff like that? The following puzzle is 2,500 years old. I am carrying a basket of eggs to market. Unfortunately, I trip and fall. Some of the eggs break, so I pick up the remainders. And when I pick up all of the eggs, one in each hand, sorry, not one in each hand, in groups of 3, my last group only has 2. When I pick up the eggs 5 at a time, my last group has 3. When I pick up the eggs 7 at a time, my last group has 2. How many eggs do I have left? What I really want to know is what number has a remainder of 2 when I divide it by 3. And at the same time, has a remainder of 3 when I divide it by 5. And at the same time, has a remainder of 2 when I divide it by 7. What I've really just done is take the linear problem we just did and turn it into a simultaneous equations problem. Now, there are two ways to do this. One of them requires me to know the inverse for these numbers in each of these mods. And this result, which we found written in several different books, but is best known as the Chinese remainder theorem, goes like this. If the M modulo pieces here are pairwise relatively prime, that means M1 and M2 are relatively prime, M1 and M3 are relatively prime, M2 and M3, M1 and M6, they're all relatively prime to each other. Then this set of equations must have a unique solution mod the product of all of those numbers. And it turns out we make that by finding inverses. I'm going to write this out in variables, and then I'm actually going to do the example we were just looking at. So the way we do this we'll let M be that number right there. And then capital MJ is little m over little mj. So that's all of them except the jth one. Those are relatively prime to one another. Then we have to find an inverse. Let's give that inverse a name, yj. And that means that capital MJ times yj is equal to 1 mod little mj. The solution to my problem, x, is the product and sum of all of those pieces. Now, upon reading this, you should most likely be going, what the is going on here? So let's go back to the set of equations we were just looking at. Set of equations we were just looking at. look like that. So according to our list of equations back up on the top of this page, these are the A numbers, and these are the little m numbers. So I have A1, A2, A3, and I have M1, M2, M3. What is little m? I wrote down a formula for little m. It's just off the top of the page at the moment. Cody?
Is it M1 times M2 equals MS?
Right, but I only have three of them. So it'd be M1 times M2 times M3. What's 3 times 5 times 7? Y'all will need a calculator for this problem. 105. And then capital M1 is this number divided by this number. 105 over 3 is capital M2 is 105 over 5, and capital M3 is 105 over 7. Give me those numbers as well. Okay, notice the step right at the top of the screen. The step says, I want to find the inverse of that number, capital M1, mod little m1. So, little m1 is 2, capital M1 is 35. I want to solve 35x congruent to 1 mod 2. I'm sorry, mod 3. Right? That's what finding the inverse is, finding the number that you multiply to get 1. I'm in the mod 3 universe. How many numbers are there in the mod 3 universe? I'm working mod 3. I really only care about 0 and 1 and 2. I don't have to do this the long way. I can do this by trial and error. Let me go even a step further. If I'm working mod 3, 35 is bigger than 3, right? Grab your calculators. What's 35 mod 3? The remainder when you divide 35 by 3. Remainder is 2. So actually solving this equation is the same as solving this equation. And the only numbers that could work in there are 0, 1, or 2. What's 2 times 0? The remainder is definitely not 1. What's 2 times 1? I was going to say, be careful here. 2 times 1 is 2. The remainder is not 1. What's 2 times 2?
4.
And the remainder, when you divide by 3, is 1. So the correct inverse is 2. That is the y number. See the top of the screen? It says call it yj. So I'm going to call this number y1. You have to do this process 2 more times with 21 and 5, and then with 15 and 7. But 21 is bigger than 5, right? So before I do anything else, what's 21 mod 5? What's the remainder when you divide 21 by 5? 1. If I ask you to solve x equals 1, do you have to do anything? The left-hand side of that is already x, isn't it? The inverse is 1. One more time. Only this time, what the hell? I don't know what just happened, people. Here we are. One more time. This time, little m3 is 7, capital M3 is 15. What happens this time? 15x is 1 mod 7. But 15 is bigger than 7. So 15 mod 7. What's the remainder when you divide 15 by 7? Which means this reduces, which means x is 1. That's y3. The answer to our question, the actual value we want is A1 capital M1 times Y1 plus A2 capital M2 times Y2 plus A3 capital M3 times Y3 mod M. What was the original value of that little m? Back on the previous page, 105. So A1 was 2. M1 is 35. Y1 is 2. A2 was 3. M2 is 21. Y2 is 1. A3 was 2. M3 is 15. Y3 is 1. 2 times 35 times 2, 140. Plus 3 times 21 times 1, plus 2 times 15 times 1. Take that number and go mod 105. I have 23 eggs. If I pick them up 3 at a time, I'll have 2 left over. If I pick them up 5 at a time, I'll have 3 left over. Pick them up 7 at a time, I'll have 2 left over. The Chinese remainder theorem is a guaranteed way to construct a solution, but it needs my ability to do inverses. If these were bigger numbers, to do the inverses, I'd have to do this process to find the inverse. These are codable. They're not trivial, but they are codable. And thus computing large integer powers or large products or even large sums can be done faster in modular arithmetic because of this than doing them directly. Like our modular exponentiation is actually faster than just multiplying over and over and over and then dividing to get the remainder. Questions? This is why you get a formula card. So you write this algorithm down, write this formula down, stuff like that. But there is another way to do this. It's not always easier. As a matter of fact, this other method, in some cases, is harder. The method is called back substitution. Which kind of sounds like something we did in simultaneous equations anyway. We would solve one of the equations by elimination and then substitute that answer back into the other one. So maybe this actually goes with that. And the answer is kind of. So here's what I'm going to do. I'm going to think of this first equation. And I'm going to say if x is congruent to 2 mod 3, then x must be able to be written as 3 something with 2 left over. I don't know what that something is, but it'll be something with 2 left over. Right? Okay. Let's take that and put it in to the next equation. X should be congruent to 3 mod 5, yes? I can subtract 2 from both sides of this equation. Hey, look, that's asking me to find an inverse. 3k equals 1 mod 5. 3k equals 1 mod 5. That's got an inverse. What number times 3 leaves a remainder of 1? Well, the only options are 0 through 4. 3 times 0. The remainder is not 2, 1. 3 times 1. Definitely not a remainder of 1. 3 times 2. Remainder when I divide by 5. Oh, well, wait a minute. That means that k, this is mod 5, k can be written as 5 somethings with 2 left over. Oh, okay, wait a minute. That means that x, which is 3k plus 2, is now 3 times 5t plus 2 plus another 2, right? Which is what? 15t plus 6, 7, 8. Now I can go to the third equation. The third equation, x must be congruent to 2 mod 7. Well, that means 15t plus 8 must be congruent to 2 mod 7. Hey, wait a second. 15 is bigger than 7. 8 is bigger than 7. Reduce those numbers. What's the remainder when you divide 15 by 7? What's the remainder when you divide 8 by 7? Which means this equation becomes 1t plus 1 equals 2 mod 7. What's the value of t? One. Which means Wait a second. Put that back here. X is 15t plus 8. What's 15 times 7? You already did this multiplication. 105. Plus 15 plus 8. What's 15 plus 8? Isn't that the answer to our friggin' problem? 23. Which of these do you find easier? The answer is probably neither of them, because you've seen them both in the last 1 45-minute period, and that's just too bloody fast to understand this. I can do this formulaically by finding inverses. But if I do back substitution, I can, for the most part, avoid having to find large inverses and don't have to do that Bézier and other algorithm, which makes my life easier. All of this, finding the inverses, finding the simultaneous equations, solving for large moduli, is exactly how modern encryption is working. There is one other theorem that comes out of this. Suppose I have a prime and a number that does not divide by that prime or into that prime. In other words, a number not 1 nor a multiple of p. Then if I raise any number that isn't divisible by p to p minus 1 of a power, I get something that's congruent to 1 mod p. Why is this useful? I want to do this problem. I could use that modular exponential crap we did last time, right? On Friday last week. A and the X and the power and go through that lovely algorithm. Blah, 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 blah. What's 13? 13 is prime. It's 13 minus 1. 121 is 10 12s with 1 left over, isn't it? When you're adding powers, that's the same as multiplying with the base, right? And when you're multiplying powers, that's the same as taking a power of a power. But according to this statement, if I'm working mod 13, every time I do 7 to the 12th, I get a 1. And that means that this is congruent to 1 to the 10th times 7 mod 13. 1 raised to any power is 1. I have no idea what 7 to the 121st power is. That's 100 and some odd digit long number. When I divide it by 13, the remainder is 7. This is faster than the modular exponential. And because I am working with a prime power, this is a faster decomposition and a faster decryption. Chapter 4, sections 5 and 6 specifically go into modern encryption behavior. If you're interested in looking at the algorithms themselves, you should read through both of those sections. I'm not going to cover it. I'll leave that to the cyber class. But what I will say is that I have a new method of proof to talk about. When we get back from break, I want to do another proving style that's based on recursion. To that end, that's the last piece of material that will go on the next exam. The review sheet is already posted. I will see you all after break. I hope you have a wonderful time. I have your last homework sitting here. I didn't pass it out before class because I ran a little